So we're going to review the layers of the inside of the Earth, and I know this is material that you've had before in elementary school, and so this probably won't take too long to review. You can see this is a cross section of the Earth, and there are 4 boxes, and then over here we have 4 labels, and based on what you know about the layers of the Earth, you should be able to take those 4 words and correctly place them in the diagram. And so I'd like you to take a minute and pause the video and just mentally think what box you would move those words to. If this is where you were going to move them, you were correct. And so here we have the crust, and you can see that the crust is a very, very thin layer of the Earth. It's the outer shell. That's the one that we walk on. Underneath that, we would have the mantle, a much thicker layer. Then underneath that, we have the outer core. We're going to learn that they believe this is made of melted iron and nickel that's churning in something called convection currents. And then here we have the inner core, a very solid, dense center of metal. Now, this crust, while it is super thin, we're going to talk about in just a minute how we humans have never dug deeper than the crust. We've never been able to dig to the mantle. You'll see this analogy often where they'll have a picture of a hard-boiled egg and a picture of the Earth. And there's a reason why these are used to compare one another. And that's because of the relative thicknesses of the layers are very proportional and appropriate. You will never have to know for this year the exact thicknesses of the layers, but you should know, which ones are the thinnest, which one is the thinnest. So for instance, if you just remember this hard-boiled egg, you got it. The shell of an egg is super, super thin, just like the crust is super, super thin compared to the rest of the Earth. Now, I know when I think of the crust, I'm like, gosh, I could sit and dig and dig and dig and dig, and I'm still in the crust. And you're telling me that the crust is super, super thin? Well, it is. The Earth is a big planet. When you compare the crust to the rest of the layers, the crust is very, very thin, much like the shell is very thin compared to the rest of the egg. The white part of the egg is very much reasonable to the thickness of the mantle. And then the 2 cores are like the yellow yolk combined, the inner core and the outer core. Now, there's 2 ways that geologists explore the inside of the Earth. One, they use rock samples. And so they drill down into the Earth and they bring back up rocks to study. And they can perform experiments on them, do whatever they'd like with them. Now, as far as that goes, we've only been able to dig 7 miles deep. We've never gotten farther than that in terms of digging through the crust. Whereas forces in terms of bringing up rock samples, I should say, forces inside of the Earth, though, also bring rocks up to the surface. We're going to learn what those forces are. It has to do with earthquakes and faults. But the Earth itself can actually bring up rocks that are buried as deep as 62 miles down. And then once those are brought up to the surface, we can then study them. Now, indirect evidence. Now, if you were kind of thinking about this, you might have had this question. Wait a minute. We've never dug deeper than the crust, but we think there's a mantle, an outer core, and an inner core. And not only that, we think the outer core is liquid metal. We think the inner core is solid metal, but we've never dug deeper than the crust. So how do they think they know that stuff? So since we've never seen it, we use indirect evidence to study the deeper than the crust layers. And geologists will use seismic waves and study the way that they travel through the inside of the Earth. And I'm going to show you a diagram of this. So if you look at this diagram, you will see that this is seismic waves, and they're just represented by a line. So it turns out when there's an earthquake, it actually releases energy, and that energy travels through the Earth in the form of waves. So each one of these lines represents a seismic wave. Now, what we've noticed is when we study using instruments how they travel through the Earth, we notice that at some times they'll start to bend. Sometimes you can see, like, especially right here, see how that bent as it went into a different layer? And then you'll see when it comes out, it bends again. And this is only showing something called P waves, primary waves. And you can see that primary waves will bend when they go through different kinds of material. And because we know the behavior of seismic waves and P waves, we know seismic waves will bend like this when they hit certain kind of materials, but they'll bend like that when they hit other kinds of materials. We also know that sometimes these seismic waves will hit a layer and they'll speed up or they'll slow down. Based on what we know about seismic waves, we know what kind of materials they speed up through and what kind of materials they slow down through. So even though we haven't seen the inside of the earth, studying the way seismic waves are traveling using instruments, we can go, oh, look, that seismic wave just sped up. Let me look at that, measure that speed, and let me guess what that material is. Now, there's another kind of seismic waves that travel through the earth called secondary waves. And those sometimes hit a layer and they can't even go through. They'll just completely come and hit this layer and then bounce out completely. And combined with that information and P waves, we can really make some good guesses.